All right, I'm back and you're back. Awesome. And as I promised, we're going to finish the first lesson or the second part of the first lesson dealing with the concept of the derivative, which is basically knowing when a function is derivative or differentiable. When is it differentiable? So f is differentiable. F is differentiable. Somewhat kind of formal, differentiable on an open interval AB if f prime of f prime of x, or the derivative of x, exists for every x, for every whatever value, for every x in AB. It kind of sounds pretty intuitive or kind of common sense, but it's differentiable if we can find a derivative for every x values in that interval. Now, it doesn't mean the endpoints. That's why it's open. So that's the only exception, because that, and I'll explain when as we do this example graphically. But this is going to be a concept they're going to test you, and it's actually pretty simple once you get this basic idea to click. So let's actually do what I like to do. I can't remember what I like to do. I like to figure this out by thinking logically. Okay, yeah. So essentially, you want to see if the derivatives from both sides of a point are the same. So let's actually make a graph. Let's do that. So let's say you have and again down low on this graph, on this plane, xy. Looks pretty good, sort of. Got this cool function from A to B. So we have A comma f of A over here. And let's throw some blue action here. Then B comma f of B. B comma f of B. So it's going to be the derivative. Hello. The derivative exists on this entire interval from here to here. Let's make some dashed lines to. I don't know why I have only 5 markers in my hand. Maybe I'm just scared that they're going to disappear. I don't. But the derivative exists all inside this interval if you can find the derivative all the time. Now, how do you do that when you're looking or doing? You can't do the math for every single one, right? That'll take forever. What you want to do is look essentially if at any point, if you were to go from this to this point from the left side and from the right side, would it be the same? Now, this is very not that's not a good example because technically this is a smooth graph, but because on a smooth graph, it's so smooth it always works out. It'd be like a horizontal line at that peak, and if you pick any point being precise, like here, coming from this side it's like that, and coming from this side it's that. So it exists all along a smooth line. But let me write this formally because this is actually not that good of an example when it's like that. So let me first show you the algebraic way to do it, and then I'm going to show you good examples when it's not. So bear with me, and I hope can understand this because haven't done this in a couple of years, but I'm doing this off the fly with no prep. So let's see what I can do. Sure, let's do the one-sided. Let's do the one-sided from the left and right. I actually like my other ones back in the day. Here we are. These are only before. So let's take a point C. Let's go on. Let's have this point C actually. That's what it's all powerful C. That C and C. So how do we know if it's differentiable at that point C? So we say the limit as x approaches C from the left side, so from this side, the negative side, of f of x, or f prime of x, is equal to the limit as x approaches C from the positive side of f prime of x. Now, again, this is not a formal way because technically, how do you know what the f prime of x is? So we just use the derivative equation or the basically slope equation. So we change this into our basic slope equation from algebra. So f of x minus f of c over x minus c. We want to make this equal to this as well, as we're coming from the positive side or right side. And again, this is hard to draw examples when it's a smooth curve. What the heck is going on with markers? There we go, x minus c. Oof. So if the one-sided limit from the left and right are equal to each other for the difference quotient, and how do we show that? So first thing, whenever you got a smooth curve, it's going to be differentiable everywhere. That's just when we say smooth, it's all like, it's all low and groovy. Smooth curve. When you got a smooth curve, the derivatives exist all on that curve. It's a good thing. It's shift flows. Like Bruce Lee when he's talking about water. So then the opposite of a smooth curve or not a smooth curve is a sharp curve where you got peaks, mountains. So what's good about this is there's not like a millions of cases you have to memorize or remember. It really just breaks down to 3 cases or 3 situations. And let's go through those. So we have when it's not differentiable. So this will be perfect way to remember what you have to look for on your calculus exam to keep it simple. So let's actually write what is up with these markers. Non-differentiable cases. Non-differentiable cases. Differentiable cases. Case 1. Case 1 will be, let's have it a sharp point. So when you have like a function like going down low again, you got something like this. See, this is like going all out of control. This is a sharp point, not differentiable here. Look at that thing. Thing's a mess. That thing's just gonna kill us, and that's not. We don't like that guy. Sharp point is the derivative will run up that way and that way. So the one-sided limits of the derivatives or the slopes would not be the same. You're going in 2 different directions. Hey, say hi to Panda. Hey, Panda. No, he actually likes it like this. He's not like he's suffocating. She's just a little shy yet. Still around, you guys. Maybe next video she'll pop out of her blanket thing. Now, the other one is when you have like a jump or a gap. So, should I just continue this? So you keep that up there? Yeah, I'm gonna erase this. Woo. So let's have like a gap or a jump. We're jumping over some like space gap. I don't know what I'm saying. I'm gonna just draw it. So we're doing this like. Then we go, and it's called a C. A closed circle here, and we go with that exact same sound. So this could be maybe C, comma, say 10 or something. And this would be C, comma, f of C. It's obviously not going to be differentiable here because they don't even connect. It's like you're trying to hang out with your buddy and like, wow, what's going on, man? You're all disconnected. So it's not even continuous. That's probably just like, yeah, you should know that intuitively. And the other case, the only really other case is where you got like a vertical line. Right, going to the extreme. Straight line. Yes. Around that flexibility, The vertical line, verticality. So, one like, okay, so the cubic function, like this guy. Actually, no, that's the wrong way. And that would be a horizontal line. What's the vertical line look like? Yeah, so like, how does it run off of? It goes, I might not remember this. Oh yeah, like this stuff. I was having a brain fart. So it intersects with 0, 0. But if you were to draw a tangent line here at this point, the tangent line at the origin of this graph would be vertical. Vertical tangent. We got a squeaky sound here. This line is is coming to life. So vertical tangent line, it just doesn't exist because it's undefined. Just like back in our algebra, middle school, preschool days, undefined slopes. It could potentially be like, or we could say sort of it's like infinity over 0. Don't quote me on that because your professor will get mad because sometimes they say, well, it's not infinity over 0, but we'd say maybe like 1 over 0 or something, and that's what we say is infinity, or the kind of the behavior of infinity. We'll get into that more later. So again, don't quote me, don't prosecute me, or cancel me because of that. But that's the idea. Infinite slope, you fall down forever. So vertical tangent line, jump, space jump, sharp point, stab someone, like jump, undefined slope, or verticality, jump. You jump off of verticality, slope, sharp point. Yeah, that's really it. Those 3 cases. Know those 3 cases and you'll be good. And yeah, your AP Calculus test life will be great. Awesome, better. So I hope that helps. Let me know. Feedback is helpful. I'm still getting into the groove of this. And I'm making example videos, or making a video where I'm just go over a bunch of examples from this section exactly. So how to calculate the derivatives using the limit process. So keep a lookout for that because those are going to be fun and intense, and those can get confusing at first. But thanks. Appreciate you guys taking the time to watch, and like, subscribe, recommend, and I'll see you guys next time, hopefully. Bye. Bye. Bye, everybody.